going to work a simple example for you here. Now this example comes straight off of my first celebration of learning from about half of the years that I've taught here at Agnes Scott, which is probably, I've probably put it on 4 or 5 COL1s, first celebrations of learning over the last 10 years. So, and every time I do it, it seems like literally half the class makes the same mistake. And it involves a difference between instantaneous velocity, or what we just call velocity, and average velocity. Okay, so here's the situation. We're down at the old drag strip, Atlanta Dragway, say, and I'm not going to draw a drag racer. I'm not going to try that. I'm just going to draw a car. Okay, it's going to go from, its initial position is going to be 0, of course. It's going to end up at x equals 300 meters. And we're going to say all 3 figures are significant. Okay, positive x that way. Car's going to start here at starting line and take off. Okay, so that's the situation. It's going to start from rest. The drag racer starts from rest, and it goes approximately a quarter mile, which is about 300 meters. And that's how far the race is. Straight line race, super fast, right from the stop. So you when you start off, you're going no speed, and at the end, you're going really impressively fast. Okay, the people who do this are, I think, a little bit loose in the brain somewhere, because it's really incredibly frightening to do, I imagine, and very risky as well. Anyway, getting on. The car is going to start from rest. It's going to go 300 meters, and we're given that it does so in an amazing 3.7. Let's say 3.70. Let's say 3.70 seconds. So we're keeping the 3 significant figures. Okay. And so what do we have? We have 2 questions, okay? So we know it's going to go 300 meters in 3.7 seconds, which again is impressive. And we have 2 things we're asking for. See, first thing we want to know is what the acceleration is. And we also want to know what the top speed is. That's how I put it in the celebration of learning. What is the top speed? Okay. And of course that means what's the fastest it ever goes. Okay, that's how I put it. Acceleration and top speed. So let's do this. Well, let me write the equations up here. Our dear friends, we have V is V naught plus AT. I meant to write these up before I started the video, but here we are. X equals X naught plus V naught T plus 1 half AT squared. V squared is V naught squared plus 2A delta X. And remember that delta X is the same as X minus X naught. Okay. Delta X there at the end is the same as X minus X naught. It's the displacement. Okay, so how do we find the acceleration? Well, let's see. We know X. We know delta X, we know T, so let's see which one of these is the best. Well, what we don't know is what the final velocity is, right? You might be tempted. You might be tempted to use the definition of average acceleration, right? Which is delta V over delta T. But we don't know delta V. We know it starts at 0, we don't know what its final speed is. Okay, so you can't use that. Now that is equal to the acceleration, because the average for acceleration, like I reminded you last video, the average and the instantaneous accelerations are the same. Okay, but that doesn't work. We can't use that because we don't know delta V. What do we do know? So we can't use this, right? Because again, we can't use this to solve for A. These two are actually very similar. But we can't use number 1 to solve for A, because we don't know the final velocity. We can't use number 3 to solve for A because there's no time there and we don't know the final velocity. We have to use number 2. So in order to find A, okay, that's the first part, find A. So to find A, use equation 2. X equals x naught plus v naught t plus 1/2 a t squared. Well, what goes away? Notice that x naught goes away, x naught is 0, v naught goes away, v naught is 0, and we can use this to solve for A because we know the final x is 300, we know the time is 3.7, so we can solve this. So if we do that, we'll get A equals 2x over t squared. We know everything but the thing we're looking for, which is A. So this is going to be 2 times 300 meters divided by time, which is 3.7 seconds squared. When we do that, we get, let's see, 43.8 meters per second squared, which is about 4.5 G's. You've heard of that phrase before? G's? That's acceleration due to gravity. This is about 4.5, roughly 4.5, a little bit less than that, maybe 4.4 times the acceleration of gravity, which is a lot of acceleration. Okay, so that is the answer to A. It was simply a plug-in. We used a single equation, number 2, and popped the answer out. 43.8 meters per second. Okay. Again, we couldn't use number 1 because we didn't know the final velocity. We couldn't use number 3 because we don't know the final velocity. Okay. So now we need to ask ourselves, that we've gotten A done, so we got A, right? A is 43.8 meters per second, or meters per second squared, and now we want to know what the top speed of the car is. Now, where is the car going to be when it's going the fastest? If it's accelerating constantly, which it is, where, let me hear you, through time, through the internet, let me hear you. Where is the car going to be moving the fastest? Where will it achieve its top speed? If it starts at rest and goes faster every instant, where is it going the fastest? Yes, at the end. So what we're looking for, this is the same as asking for V. It's the same thing. Now, here's what happens to students when they're in an exam, or they're celebrating, I should say, and they get a question like, what's the velocity? They want to know what the speed is. And they look at what they know. They know, they look at what they're given. And a lot of times what happens when you're in a timed situation, like in a celebration of learning, is instead of, and this is not a critique, this is just what happens, I know because I've seen it happen over and over and over again, is you look at what you know and look at what you need and you try to plug in what you know with what you need without really thinking about what equation you're using and is that equation the right one to use or not. And what often happens in this point, when you get to the top speed, and actually the top speed, students simply look at what's given. They look at x over t, and they think that the velocity is simply x over t. Okay? And so they plug in their numbers. This is 300 meters, and this is 3.70 seconds. And so when they do that, what they get out of that is, let me see here, Let me actually divide this right now with my calculator. I've left a significant figure off with my notes, so let me do this real quick. 300 divided by 3.7. 81.1 meters per second. They see a distance, 300 meters. They see a time, 3.7 seconds, and they give me this answer. But that answer is incorrect. Because what this is, right here, listen closely, this formula that they used is exactly the same as the formula for the average velocity. Look at the formula for the average velocity. And because both x naught and t naught are 0, this is the same as x over t. What they give me as an answer is the average velocity. This is not the final velocity. This is the average velocity. When you divide distance by time, displacement by time, that gives you the average velocity, not the final velocity. Okay? So don't use that. Okay? Just because I gave you 300 meters in 3.7 seconds doesn't mean that the velocity is the ratio of those two. That's the average velocity. So this number here is v average, not final velocity. And what I'm asking for is the top speed, the final velocity. And once you have that, you can see to find v, you simply use equation 1. V is v naught plus at. V naught, as you know, is 0. A we just found, so it's 43.8 meters per second squared times the time, which is 3.70 seconds. And what you get as the final velocity is 162 meters per second. And that is the right number. Final velocity. Top speed is 162 meters per second, which is about 350 miles per hour. Boom! In 3.7 seconds. 0 to 350 miles per hour in 3.7 seconds. It's pretty impressive, but that's the answer. Okay? Now, I'm going to say one more thing about this. I think I'm going to put it up here. The alert among you, actually probably nobody noticed this, but maybe somebody did. The alert among you will have noticed that the actual top speed, 162 meters per second, is exactly twice the average velocity. Right, this is the average velocity, not the answer to the question. That's the answer to the question. But if we plot velocity versus time, okay, what happens in the situation is this. You start off at time t equals 0, at no speed. The velocity increases at a constant rate. So that when you get to 3.7 seconds, you are moving at 162 meters per second. Your velocity has increased steadily the entire time. Notice that when you started here, your velocity was 0. What's the average of the final and 0? It's the midpoint, right? The average of two numbers is the number right between them. So the average velocity right here, that is 81.1, or to say 81 meters per second. That is the average velocity, and that is what is calculated with a simple v equals x over t formula. Okay, so it achieves its average velocity at the halfway point in time. So this is 1 point, what's the number? That's not right. Yeah, 3.5. Of course, higher math. 7 divided by 2 is 3.5. So at the halfway mark in time. Okay. So the slope of this is constant because the slope of this line here is equal to the rise over the run, right? Which is 162 meters per second over the run of 3.7 seconds, which is 43.8. In other words, the slope, and I've said it before, but the slope of a v versus t graph equals the acceleration. So what you're doing when you use the simple v over equals x over t is you're finding the average velocity, which is halfway between your initial, which is 0, and your final, which is 162. And that is the final answer, 162. All right. That's it. Next time up, another example, was it? What do we have next? Yes, another example, this time of free fall.